and welcome back to the notational hell that is exercise 1 in chapter 6. What we want to do now is express theta hat using m1 and m2 and x. The first thing that we may notice is the mean of theta is m1, so we're kind of safe there. The second thing we may notice is we are not safe with regards to this term, and this term. So it is a good idea if we take a small detour out of this calculation and just calculate the different things that we have. And I actually recommend we do it out here because we might actually use some of this stuff later on. So what is it we want to look at? We want to look at, maybe we should start with the mean of x. Now we go back a couple of weeks to the conditional expectation rules that we learned. We will use the rule of double expectation, where we take the expectation of the conditional expectation of x given theta. This is the definition of a conditional expectation of x. So by assumption, x given theta is Poisson distributed, hence the mean of x given theta is theta, and this is just equal to the mean of theta. And that's nice because this is equal to m1. So we've taken care of the mean of x. Let's also take care of the variance of x. Now, let us note that the variance of x, well, we can do different things here. The thing that I want to do is kind of recall the formula of total variance that we learned before so that we keep all our earlier skills well used. So the variance of x can be split up into the mean value of the variance of x given theta plus the variance of the mean value of x given theta, right? This was the formula of total variance, I think, that we used or we proved in one of the earlier exercises. Now, since x given theta is Poisson distributed with mean value theta, the inward here is equal to theta and the inward here is equal to theta. So basically what I have is the mean of theta plus the variance of theta. Now the mean of theta is quite clearly m1 and the variance of theta is the second moment of theta, which was m2, minus the first moment squared. I mean, just by definition of variance. So now we also have an expression for the variance. Last of all, we need an expression for the covariance of theta and x. And this is also very good that we have to calculate this because then we can kind of brush up on the definition of covariance as well, which we will be using a lot in 1b. So the covariance of theta and x is by definition the mean value of theta multiplied by x minus the mean of theta multiplied by the mean of x. Well, I mean, among many definitions, this is one of the definitions. The last term here, mean of theta minus mean of x, we actually already know what that is because mean of x is m1 and mean of theta is m1. So the last term is just m1 squared, right? So it's actually the first term that's interesting. We write up the first term using a double expectation again. So this is equal to the mean of theta x given theta, and I take the condition. I take the expectation of that. And what I see here is since I'm conditioning on theta, I can take theta outside of the inner conditional expectation. This is a rule called taking out what is known. So if I condition on theta, I can take anything that depends directly on theta outside of the conditional expectation. So I will have the mean value of theta multiplied the conditional expectation of x given theta minus m1 squared. Now what I know is that the mean of x given theta is theta. So what I have written in the first term is the mean of theta squared, which is the second moment of theta, which is m2. So I have m2 minus m1 squared. Now I have I have expressions for each of these three based on M1 and M2, and that is nice because that means I can continue my calculations up here. Mean of theta is just M1 plus the covariance, which was expressed by M2 minus M1 squared, divided by the variance of x. So minus first, so or divided by the variance of x, which is m1 plus m2 minus m1 squared. And then I have to take this fraction and multiply it by x, which is just x, minus the mean of x, which we established is the mean of theta, and that is equal to m1. So now I have an expression for theta hat. And if you recall the expression that we found for theta hat using the formula for linear Bayes estimator in the Buhlmann model, then it was exactly the same as what we get here. So yay, that's nice. Let us also just write up the risk of theta hat calculated using Formula 618 from the general proposition. So it is equal to the variance of theta minus the variance of theta hat. Now the variance of theta is just the second moment of theta minus the first moment squared, whereas the variance of theta hat is equal to the variance of this entire thing that is theta hat. Now, one thing that you have to always remember with variances is that they are translation invariant. That means that no matter whatever I put inside the variance, the terms that contain only deterministic constants, they can just disappear inside the variance. So that means that this term disappears, and also, so this is part of the fraction, right? When I take this fraction and multiply it onto m1, the part with m1 will disappear. So the variance of this huge entire thing is just the variance of this thing here. And also I can take constants outside of the variance as long as I just square them. So in conclusion, the linear risk is given as m2 minus m1 squared minus the square of m2 minus m1 squared, so this thing squared, divided by this thing below squared. So I have to take this and square it, and then I multiply by the variance of x. But now just notice that the variance of x is expressed using m1 plus m2 minus m1 squared, which is exactly what's in the denominator. So one of the terms down here that was essentially squared will cancel out with this term in the numerator. So this is what we're going to end up with. So this is the risk of theta hat.